Okay, let's start. Today is the last lecture on to cover the last part of the content of Solar 2X. And today we'll be talking some more of easygoing topics on how we use the Solar 2X technologies to solve not only the energy crisis, but also water, food, and also environmental. So I wrote this here wrong. It's not V5, it's VFE. So the last E is environmental. So water, energy, food, environmental. Okay. And before we start, let me recap on the most important thing about creating renewable fuels is not just the energy itself, but also the resources. And I can't stress this enough because it's something that people don't talk about it so much, don't think about it so much, but I think it's the most important thing to move forward to make renewable fuels is the renewable resource. And when we think about making renewable fuels, we need to look at, not only the energy part, the energy harvesting part, but also the resource that we're going to be used to make that fuels, like fresh water, seawater, biomass, CO2. And so when we design or when we decide the location of the plant, we have to consider all this. You know, in Thailand, I yeah, I talked to many people about Thailand and try to encourage the government actually to think of the renewable fuels as a new goal, new fossil fuels of Thailand, because although in Thailand we don't have, the fossil resources, but we do have a lot of water, a lot of flat land, and we have plenty of sun. So hopefully, if we can make this some technologies more commercializable, then we might be able to export energy to our neighboring countries, and that would create a new S-curve economy for Thailand. But what you have to know here is just that resource is very important and the location as well. As this is also recap from our previous lecture where we talk about, different metrics that is important to design the solar projects, right? You have to think about the availability of the sun, of course. You have to think about the space that they have, the resources like water and CO2, and the energy demand for different seasons. If the goal is to store the energy during the off peak time, like in summer, and to use it in the peak time, like in winter, then we need to look at the the aspect of the energy requirements for different regions so that we can design the right renewable solution for them, right? If if in Thailand, for example, maybe it's not turning the solar energy into fuels might not be the best short-term solution, for example, because in Thailand we use most of the energy for cooling, right? It's for daytime. So the daytime you already have sun, the nighttime, well, you don't need much cooling. So maybe the energy used can be used directly to cool down, our household during the daytime. But that's also not 100% true because a lot of us use, energy at home at night. So yeah, there is those things that we have to take into consideration. But for Europe, it's very clear that they need right now, for example, in the UK, they use a natural gas pipeline, which is very weird. Instead of using like individual heating solution, they have the gas pipeline going through all the household to heat up the house. So that also. So when you pay the electric bill in in UK, you pay both the gas and also the electricity, and that costs a lot as well. For it's not really efficient. Okay, and this is a recap on the land problem that we talk about. When we want to deploy the solar harvesting farm, I'm not talking about just PV, but also solar fuels devices. You need a lot of space. And if you go into calculation, you will see that many of the country will suffer the land scarcity and also water scarcity. So we have to think about that. That's why WiFi nexus or water, energy, food, and environmental nexus is very important because it's govern our thinking about creating solution. Let's focus on energy part here, right? If you look at energy, because we are chemical engineers, we I guess the energy part is what we are interested in, but it also relates to other sector, right? If we want to make energy, maybe we take up space for food. If we want to make energy, maybe we use a lot of water to make hydrogen, for example. And in some country, water is very scarce. In some region, you can't find fresh water. So that's something we have to think, and as well as the land resource that we need to use. So the outline of this lecture will go through 4 different topics. One is the So all of this we focus on the energy part, and then we touch on the other nexus. For example, the first one we focus on energy, but then that is the topic that is related to water. The second one related to land and space. The third one related to environment. And we have some case study that I would like to show. Right. And the last one is some miscellaneous other solar to X harvesting technologies and future perspective. Right. So let's first identify the problem about energy production and water. So maybe try to understand these 3 topics. Right, the first one, there are solar energy but no water resource to make fuels. Right, we know that more sun equal to less water, more evaporation. So that's the dilemma that is true for most of the region, right? And some region, even if there is water, but turn out it's a sea water or it's a water that cannot be used directly and require a lot of energy to desalinate or to purify. The second one is the poor quality of the water in the rural area, making decentralized renewable fuels difficult. We all heard about Elon Musk off-grid house, off-grid home. Many people in the USA try to go off-grid, right? And off-grid idea is very important because it's very exciting because you don't have to rely on the centralized facilities. You can make a unit that can sustain itself off-grid and go anywhere in the world. And that take away also the burden of the government to provide, all this facility, all this infrastructure to the rural area, and that help expand the development or the economic development beyond the city center. But as I mentioned, we need both energy and resources. So energy can be decentralized. You can put solar cell anywhere, but resources like clean water, maybe not so much decentralized. Like most of the reverse osmosis facility is very centralized and very big scale. So yeah, when we think about the decentralization of the renewable fuels production, we have to think also about the resources. How, if we want to go decentralized, what kind of resources can we use? And the last one is competing water resource with food and residential and the energy sector. So the water is used for everything. We have to think about that resource competition and how we can optimize and minimize the impact, the social, the environmental impact to the water. Not only us, all the ecosystem rely on water, fresh water, which is only 2 or 3% in the world. Okay, I'm gonna start with the case study of my own work during my time in the UK. So this work is inspired by this question, right? This question. So this is my friend, Dr. Motia Rahman. He asked me in 2019, can we make hydrogen from seawater due to lack of ultra pure water in many regions essential for hydrogen production? So he's from India, and he said, yeah, in his country, if you want to make hydrogen, there are a lot of investment that needs to be implemented for the water purification. So can we make hydrogen directly from seawater? So at that time, I thought, maybe we can make some kind of integrated system to do that, because the reason why we can't use seawater directly is that just like we cannot drink seawater, seawater contain a lot of salt and it will mess up our body so much, right? Similar to catalytic system, if you have seawater, it will also mess up and kill, deactivate the catalysis that is needed for hydrogen production. So most of the electrolyzers that we heard about is need to use deionized water, need to use RO water. So that's why this topic is something that I was thinking. So I drew this in 2019, thinking, oh, why don't we create some kind of like a hybrid system where we use we use the solar vapor generator. We already know that vaporize the water. And then we put the photocatalyst on top, right? Photocatalyst will not touch the water underneath directly. So any contaminant will be rejected and will not reach our delicate photocatalyst. But the photocatalyst will only absorb the gaseous water vapor that pass through, our first evaporation layer. So that was the idea that I proposed in 2019 after my first year of the PhD. And I proposed to my professor then, Professor Erwin Reisner, and he said, okay, let's go for it. Let's try. So at that time, we tried and then we came up with a paper, and this is how the system operates. So you will see that as I mentioned, the solar light is for photocatalyst, it can only utilize UV light and a bit of visible light, but the rest of the light is lost. And is a very wasteful process. So we want to utilize the whole spectrum. So this how we demonstrated here. So we have solar vapor generator absorbing most of the light that cannot be absorbed by photocatalyst, vaporize the water. The water vapor pass through the photocatalyst layer, which we optimize to get the most efficiencies. And then the photocatalyst absorb UV. So in this way, we can absorb most of the light to make hydrogen from seawater. And then this only account for less than 1% of the water that is being vaporized. The rest is being condensed and turned into distilled water to be consumed or to be used for agricultural activities. So that's the device that we designed. It looks like this. Very thin sheet of device. So we use like a carbon paper kind of device. We coat it with hydrophobic surface, so to prevent the water from going through. So we want to keep the catalyst dry and not touching any of the seawater underneath, right? And as you can see here, the light absorption is complementary. So our photocatalyst itself absorb only UV light, while the carbon paper absorb most of the light. So here we can see that most of the region of the solar light it can be utilized. And we also design, the reactor to collect the water and also to collect the gas, hydrogen. And with this design, we call it artificial lotus leaf. So it's just look like a lotus floating on the water. And the vaporization mimic the water, the plant respiration release of water when it does like a photocatalyst, when it does the photosynthesis. Anyway, because of this design, it's quite versatile in terms of the substrate we use for making hydrogen. So traditionally, we can only use the clear, transparent substrate to make hydrogen, because if we put the powder inside the solution and we disperse it, we don't want the solution to be black to block the light, right? We want the solution to be just water with some molecules dispersed in it. But in our case, not only we can use it with seawater, but because of the catalyst is floated on top, so it absorbs most of the light, and the solution underneath can be anything, right? In this case, we take the lignin containing solution from AA, no, I mean not AA, but from the paper company that, they have a lot of this lignin containing wastewater. We use that to make hydrogen. And at the same time, we reduce the volume of the water, of the lignin containing water, so that it's easier to manage, right? So you can imagine the paper industry, they produce a lot of wastewater because making paper needs a lot of water, right? So this device not only making hydrogen, but also help vaporize that wastewater and make it easier to manage. Okay, this is how the layer looks. So this is the carbon paper that I talk about. And then on top is the photocatalyst layer that we optimize for the maximum performance. So this is how we do, right? We vary the catalyst loading, right? This is the milligram per square centimeter. And then we see the performance going up, obviously, because of the more catalyst, thicker layer for the gas to pass through. But we can see some kind of plateau if we put a bit, if we put a lot, and we have to also consider the trade-off between the catalyst amount that we load and also the, what is this? The solar to the amount of hydrogen per gram catalyst, right? So obviously we get higher performance, but per gram it become less efficient. So if our catalyst is expensive, we have to find the right spot that we get both, the good performance per gram of catalyst and good performance overall per area of the device, right? So we choose 2 milligram per square centimeter as our optimized catalyst loading. And on the solar vaporization side, we produce about, you can see here that in the blank, without any floating device, the water already naturally evaporate under the sunlight. So it's about 0.5 kilogram per meter square per hour. But when we put this black device on top without any our photocatalyst, it produce about 1 something. And then we do the loading, right? So you can see the more we load, the less water we produce because of the blocking of the sunlight, and because of the UV blocking and also the light scattering, it get reflect on the surface. Because as you can see here, our surface is white, but the performance doesn't reduce that significantly. You can see here, our optimized process, we still get quite a good amount of water. And this is how it looks under the thermal camera. You can see that when you radiate the solar light, the surface of the device heated up compared to the surrounding area. And so we test our catalyst against 3 different variants. One is we put, instead of floating, we put on the glass substrate, like traditionally people do. And you can see here that under in pure water, it produces very good amount of hydrogen, but as soon as we put it in the seawater, the performance degraded very quickly. And this is what I'm talking about what I talk about, where the catalyst get degraded and get deactivated with the salt being present. So the second approach we do the same, but without hydrophobic coating in the middle, right? Without hydrophobic coating, we see the performance decrease as well. So that's quite unfortunate, showing that if you just put carbon paper, put the photocatalyst on top, the water pass through and deactivate the catalyst the same way. But the third one, after we put the hydrophobic coating, we can see the performance boost up to very similarly between with fresh water and with seawater. So we were very excited about this result. And of course, when we test the hydrogen evolution, we also have to test the oxygen evolution. Because if the molar ratio or the mass balance doesn't match, then we don't know actually if the whole process is really water splitting or not. For example, many people only report hydrogen and they don't report oxygen. So we don't know whether the oxidation part is maybe it could be organic oxidation that we talk about in our previous class rather than water oxidation, which are much harder to do. So here we show that the molar ratio of the hydrogen and oxygen is 2:1, as expected for the water splitting reaction. Okay, and we also tested this device under different light intensity. So you can see here that the solar to hydrogen efficiency increases as we increase the light intensity. And this is very nice because normally we would expect, well, not normally, but as you can see here, the hydrogen production, it doesn't go that linearly. So we think that there is a synergistic effect between this approach, between the sunlight intensity and our device performance, because normally what you would expect is the linear increase, right? But here we think that the more sunlight hit, the more vapor is being generated, the better the performance of the device. Right? And when you do this kind of solar vaporization, if you want to propose this kind of solar vapor generation in your future projects, this is one of the key parameters, right? When you vaporize the water and you collect the pure water, you have to test for any heavy metal, any ions. And here we can do that by ICP, OES, or the ionic some kind of chromatography. So this is a standard, right, for the WHO and EPA standards. And you can see that the raw seawater, for example, has very high concentration of all these things. But after you vaporize it and you condense it, you get this ion left over, which is way below the threshold, the regulation threshold. So it can be considered as usable or safe to consume. Not only we try with seawater, but we also try with different kind of water, like fresh, like a river water, and also turbid waste, like I mentioned from the paper industry. And the performance is very similar. And this approach is quite scalable because it just drop casting the photocatalyst on the carbon paper. So you can make larger device very easily, and the performance doesn't drop because photocatalyst is very scalable. There is no like a drop there is no current collection like in PEC. PEC, you need to make charge and you have to collect the current somewhere, right? But here everything happening in the molecular level at each particles. So no matter how large it is, the performance will still remain the same. So it's very scalable. And we also test the long-term stability. And as you can see here, so with typical photocatalyst on the glass substrate, you see initial higher performance, but then the performance drop rather quickly. This is on the top one is the fresh water. So in fresh water, the PEC, the traditional one show higher initial performance, but then drop. our device actually run quite stably, right? And under the seawater, we don't have to talk about because other device cannot really perform under the seawater, but why our device actually perform really stably over 150 hours. Okay, so how we can use this in future? So at the end of the project, at the end of the paper, we propose this kind of scalable floating system where you can see here that the device itself touches the seawater, vaporize. We collect the water to be sent to the shore. And then in this chamber, we also collect the hydrogen gas to be processed and used or stored, right? So yeah, you can think of the system being utilized something like this offshore, and we will come to talk about it more in the next slide. So that's the end of the project, and before we finish, we thought of another idea. Remember when I talked to you about the solar to chemicals, where we replace the water oxidation with substrate oxidation to lower the energy requirement for fuels production. So we think that maybe we can utilize the light even better. So we might put the same material that only utilize the UV on top, the most top part. The second layer, we utilize the photoreforming or the coupled reaction where we oxidize the organic substrate on the other side. So we can think about this as a full solar spectrum utilization, right? And then on the bottom part, we don't have to produce oxygen anymore. We oxidize the organics, right? So we get the hydrogen from the middle layer and also the top layer. So the really the whole spectrum can be utilized. So that's the idea that we left with the team at Cambridge, and I left for Thailand. So I'm not sure whether some people work on this more or not. But yeah, we will revisit this idea at some point. So this is the image from the recent review papers on this solar. They call it the interfacial evaporator, but it's the same thing as the solar vapor generator that I've been talking about. So they summarize it very well on how this technology is being used for in nowadays and what are the limitations. So I already put the paper in the my course view. If you're interested, feel free to read. So you can see here one of the key significance that we have to think about is when you design the window like this for the water for the vapor to condense, right? Normally, if you use just a glass substrate, the water will form like a water film, large film, and it slowly drip down. But that's the problem because the water block a lot of the IR light. 1 centimeter of thickness of water already block. I don't know exactly, but at least 50% of the IR that can go through. So the water molecules, as you know, it's the same principle as microwave. The water molecule vibrates a lot when I mean react with IR light a lot. So meaning that it absorbs a lot of IR. So when you make the material for this window, you have to think about using different kind of surface to make a small droplet and make it drop down as fast as possible to prevent the light blocking and so on. So yeah, these are different way development, and these are the prototype of like a floating water harvesting in the ocean. Okay, that's the case study 1, where we talk about producing energy and linking to the water. And this is the case study 2, really quickly. So making energy can also solve the water problem, right? If you talk about decentralized PV deployment, And instead of taking up the land, you put it on the water reservoir, right? These are the water reservoir that every agricultural land has. When you do the rice farming and so on, you need to have this kind of water reservoir to be able to flood the field, for the small young sprout to go out and to remove all the weed, what do you call วัชพืช ใช่ไหม but you can think about that, right? If you have this water and it keep vaporizing all the time, it's really bad for you, because sometimes during the drought season, there is no water for you to do agricultural activities. So deploying this kind of solar farm could help minimizing the evaporation, right? So it keep the water for longer, and at the same time providing you with electricity. So it's a very smart idea, and many country is now deploying this technique to preserve the water. Like in some country in the canal, in the city canal, they float this kind of panels, right? To preserve the water and also to help condition the water underneath. Okay, now we go through the first part of the lecture, and now we're going to be focusing on the second part, is the space, right? The energy production related to space. So as I mentioned here, space, meaning the solar receiving area, is limited and won't be enough for food, businesses, residential, forests, and so on. So we need to find a way to preserve those space. And we talk about this, we touch on this various times during our previous lectures, such as the utilization of concentrated solar light to reduce the space we use, to go a little bit beyond the city center in order for energy production, so that we reduce the space, that the competition between the economic development and residential area. So let's go to the case study, right? And this one, I think everybody should have heard about it. It's called agrivoltaics or agrophotovoltaics. And I would call this in short APV, right? So the concept is very simple. And this is driven mostly by Europe, the problem in Europe, because in Europe, as I mentioned in this picture, in Europe, they don't have space. You can see here, this is Europe. Most of the country has the problem of land scarcity. They don't have enough space, but the economy is so developed, right? So they have to find a way to be, and they don't have space for agriculture, so they have to import their food. And you can imagine that when you import the food, you reduce the country food security, right? That's very important for any country, like what Trump is trying to emphasize. Our country, we are proudly say that we are food secure, right? So Europe, they are driven by this problem of lacking of space for agriculture. So, and they also want to go green. So they came up with this idea, right? Where if you look at this photosynthesis rate against the irradiation level, you can see that there are two kind of plants broadly, right? One is the light plant that you use a lot of light, and another one is a shadow plant like berries, strawberries that doesn't use so much light and like to go under the shade, right? So for any plant, it's the same thing. If you add too much light, if you give it too much light, there will be some saturation point that it cannot utilize the light even further, because now it has to respire a lot of water, and it might burn, it might die. So you can see here, this is called light saturation point. And because of this, we think that, okay, if we have the solar panel, instead of putting it on top like this, we make a little bit of space between the panels, let some of the light pass through, and control the light underneath the panel to like 50-60% according to the requirement for the certain kind of plant. Then we might be able to increase the land use efficiencies. And what is the land use efficiencies? You can see here, this explained really well. If you have the plant growing, let's call this 100% land use efficiency. If you have the solar panel that is very optimized for solar energy harvesting, that's also another 100%. So if you talk about the land use efficiency of each piece of land is 100% in the reference part, right? But 100% is not enough, right? We want to increase that to 200%, right? To closer to 200% because we don't have enough land. So that's why you lifted the PV up like this. So obviously some plant will grow a little bit better, some plant will grow a little bit worse. The solar panel compared to the reference will be a little bit less because you put some space in between. So per area, it will harvest less energy, but after all, overall, if you combine the two, right, you can increase the land use efficiency, by 80%, for example. So that is really appealing for European country. And there are also another benefit that we will talk about, but here, not only increase the land use productivity, but some plant might love the shade and grow even better, right? As I mentioned in our previous slide, PV doesn't like heat, but when you put it like this, as the plant, release the water vapor, it can also help cool down the PV panel. So that might increase the efficiency as well. And obviously reduce the water usage, maintaining the high soil moisture because it doesn't vaporize so much. And then another synergistic effect. So this is the summary from this paper. I won't go into the detail, but you can see here that all those benefits that I mentioned before, I like to highlight maybe one thing here that you can see that it affects not only on the yield, but also on the temperature. So you can reduce the temperature of the farmland by 2 to 5 degrees by doing this. And what it means is that you create little greenhouse for your plant. So maybe the coffee beans that is now grown on the mountain that has lower temperature now can be grown in the flat land in the city where everything is much easier, lowering the cost, for example. So, there are some economics opportunities when you're deploying these things. And obviously save the water. Okay, let me show you the classification of the APV. So there are two kinds if you separate it broadly. One is alternate land use. So you have like a PV like this, and then you have a space in between. So this is the more traditional way of utilizing this space. So it's not really directly on top of each other. But this is very good because traditional equipment can go through and you don't have to change much of the equipment, and the panel doesn't have to be really high. It can be like normal one, but just leave some space for the plant to be grown. And the other one that is more exciting is to lift the panel up a little more and to do this dual layer space use. But the problem with this is the cost, right? So you have to put up this big infrastructure for the trucks to be able to go through and harvest your equipment, to harvest your produce. So these are the two main categories. So when doing this kind of thing, obviously the cost of the equipment and the new kind of investment has to be considered. And as I mentioned, structural integrity is very important because you don't want to invest so much on putting, the pillars and everything to make it withstand the wind and the nature, right? So this is some of the example of the structural innovation that they came up with using this kind of needles, like to put it under the ground so it acts like a root of the trees to make it quite strong and withstand the wind and storm. So this is the case study in Germany. So this company they try this, so they want to know whether it doing this is useful for the country or not. So they try this. So in order to understand, they have to have the reference field. So they have the reference of the traditional solar panels to see in one area how much electricity can be produced. So that would be the 100% land use efficiency, right? That would be the reference point for the 100% land use efficiencies. And then they have also the reference field where they grow the shade plant like strawberries, and normally when you grow this kind of plant, you have this plastic cover anyway, right? To prevent the bug and so on. So this is their reference field, and this is their 100% land use efficiencies. And this is the experimental field where they have the solar panel on top of the same and growing the same plants. And skip through all the experimental ways, methods. The result is that in 2 consecutive years, they find the land use efficiencies of about 1.5 to almost 1.9, meaning that you can, by doing this, you can increase the efficiencies of the land used by almost 100% one time. And the light shading here represent the electricity. So the electricity obviously is decreased from the reference. If the reference is 1.0, by leaving some space, you get about 0.8, which is not bad, right? And then the plant, if the plant growing under the reference field is 100, growing under the sunlight is reduced by a little bit, or not even reduced. Some of them even grow better. So combining the two land use, two products, electricity and crops, they can come up with this number of like, 156 to 187% of the land use efficiencies. And not only that, they found that the irrigation water usage is reduced by 50%, right? So that's very exciting for them. And also they create some kind of, as I mentioned, microclimate or greenhouse effect underneath the sunlight. So the plant is actually protected from the weather and can grow better in the harsher climate, right? Another one that I would like to mention, for me, this is more exciting because this is more scientific, right? They put the solar panels, but not the traditional solar panel, but the solar panel, the organic solar panels that is not fully, what do you call it? It's partially transparent, right? So organic solar panel can let some light pass through. Like for example, this one can let most of the light in this region pass through, right? This organic panels. And then they grow some spinach, basil and spinach underneath. And what they found is that they found that the spinach, when you sell the spinach, you sell the leaf, not the roots, right? So they found that the total biomass, although decreased when you put the when you put the panel on top, but most of that decrease came from the decrease of the biomass. So if you take the total amount of the plant as a biomass, the biomass decrease, but most of that decrease came from the root, that the plant doesn't need to produce that long root to find water, because the solar cell help keep the water in the soil. But then you can see here that, and also it doesn't have to go so tall, right? But what happened here is that the leaf itself grow larger, and that is induced by the reduced light coming through the plant. So the plant is kind of stimulated to make the leaf a bit larger to absorb more light. So by playing with this tricks, you can get the higher yield of the sellable product, right? Instead of putting so much energy to grow roots and the stems, you grow the leaf instead, which can be sold for for higher cost. So that's one of the example, right? And it's the same story for basil as well. So this is very exciting, and they also found that by creating the stress for the plant by filtering some of the light, the plant actually produce more protein, right? So this kind of like investigation need much more research and development. But I think this is a great opportunity for Thailand, because as we say, we are the kitchen of the world. So if we can optimize all these things, right, we can really make our plant a little bit more nutritious. We can make our plant a little bit taste a little bit better while getting the energy at the same time, doing this. So this is my idea. Maybe we can utilize the photocatalyst panels. The what we learned from lecture 4 with the solar to chemicals, right? Not doing half reaction of making hydrogen and another half reaction of doing oxidation of like the organic waste present in the agricultural water. So all this agricultural water has a lot of organics and nitrates. So if you cycle this water through the panels, making hydrogen, and also at the same time filter out the extra nitrate that is bad for the plants and cycle it back to the plants. Maybe this could be the circular design that help us to not only get the energy, the fuels, but also grow our plants underneath a little bit better. So that's the idea I would like to leave you with. Another thing for this topic that I would like to talk about is the cogeneration of water and food. And I will touch on this very briefly because it's quite obvious. So this paper summarized very well on how this how this sector help water and the food related, and here are some of the design of how we can use the seawater or the industrial wastewater to grow plants, right? So the first idea is similar to what I already talked about. Vaporize the water, collect the fresh water, use it for agricultural waste, use it for agricultural activities. Another one similar to what I talked about. Here are some of the idea where they vaporize the water directly onto the soil over onto the top and then grow the plants. So this, you can imagine this system used for Saudi Arabia or some country where they have vast area of the ocean, but they don't have the land for agricultural activities. So that can be used. And this chart also summarizes how the light is being used for different things, right? Similar story as what I discussed. The IR light used for desalination and the solar energy in the visible region used for photosynthesis, right? Another way you can harvest. So this is called Trinity food, right? But it's just a far-fetched idea that what they do is they have the salt water on this side, fresh water that is being produced on the other side. And when you have fresh water, salt water, this experiment when you were young where you have the orange and then you put 2 electrodes and then it makes some kind of electric circuit. Similar thing. They have the seawater as the input and then they produce fresh water, and in between is a membrane. And because of the different in salt concentration, it makes electron go one way. So they said they can produce electricity from this salt gradients, right? And at the same time, they can produce fresh water for germination, sprouting of the seed, and also for cultivation. Another idea here is to use like a floating evaporator. And when you evaporate the water, basically the nutrition, the salt stick onto your evaporator in this capsule, right? It's absorbed and sit where the water is being evaporated. And you can imagine is this ball as a nutrition rich ball. And when you're done with the evaporation, you can put this ball into the soil and the ball break down and release the nutrition back to the soil. And that could be one idea of solving the Wi-Fi nexus. Another idea here is to solve the problem of the din kem salty soil in the disaster affected area, like in Tohoku. After the tsunami, the soil became very salty and cannot be used for agriculture. So they came up with this idea where they vaporize the water and use that basically free fresh water to flush the soil constantly, and to remove all this salt, so that they can recondition the soil to be used later on. Well, the next case study is my recent papers that I already mentioned. So one of the things that is very important for the floating aspect of the PV or other thing is as I mentioned, the reduced evaporation, right, and the reduced land use. But for solar fuels, the left one is just energy production, right? The right one is for fuels production. So you need another thing, resources, right? And those resources mostly are water, industrial water, and so on. So by floating your solar fuels on the water bodies, it's not just help, get the benefit similar to the floating PV, but also you have direct access to the resources underneath, like water, wastewater. And this will help to answer the first question that I asked you about the decentralized energy production, where we have to find the decentralized or suitable resources as well. So you can see here that, right, if you float this kind of solar fuels panel, you can access the water underneath, going through the filter pump and then feed directly to the panels to be used for feedstock to be used for making hydrogen. Or in this case, we can float this device directly on the industrial wastewater, feed the carbon dioxide from the direct air captured CO2, right? After you fed the top part used for making fuels, and the bottom part, the whole is used for oxidizing the organic substrate. And that goes to show how this system is going to be used in the future. And the last topic before we end our lecture today is about the energy related with the environmental nexus, right? And this is similar to what we talked last time when we want to produce, when we want to develop any kind of energy harvesting device, we utilize a lot of mineral and rare earth metals. So, and that is harmful for the environment. Another thing that I will not discuss today, but you can imagine, for example, I mentioned that you can maybe put the PV panel in the desert, right? In Saudi Arabia desert. But when you put the panel, it creates the shading. It creates the lower temperature underneath the solar cells. And what happened is you change the natural habitat, right? Maybe now there would be some animal coming to live under the solar cells, right? And 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 so it will also mess up the ecological system, right? The predator might come closer to the city where the panel is being installed, because it's now has a shading or the hiding place for them. So these are the things that as a engineer, as a scientist, we have to think about when we want to do any of these projects, right? We have to talk to the stakeholder, we have to evaluate the environmental impact on our installation, right? Or that you see the picture of the solar concentrator, right? Imagine if the bird fly over that concentrator, it will just be burned, right? So these are the things that we have to think about. But today I would show you just one case study on using the solar vapor generator to harvest the rare earth metal. So traditionally, to harvest the lithium and other rare earth metal is very difficult because you have to dig into the mine, and lithium mine is very harmful. Any mine is bad for the environment. You have to dig down. You release many carbon dioxide while you dig. You do a lot of things to the earth, right? But this simple idea, what they try to do is they try to harvest the lithium from seawater. So lithium in seawater is really has a really low concentration, but ไปไหนอ่ะ
ไปกินขนม
มันไม่กินเลยเนี่ย
เขาไว้กินขนม
Right, so the lithium, in this case, they developed the really long string like this, and when the seawater vaporized, because of the different solubility of different metal, right? Because of the different solubility, the crystallization happening of the sodium chloride happening at the lower area, but the lithium chloride crystallization happening on the top. And this simple idea you can use to harvest, lithium and use for batteries and so on, right? And this is how easy it is to harvest the lithium chloride. So you can see it form this kind of crystal structure on the top part, and they can just peel it off like that. And this lithium chloride can then be processed and make lithium for making batteries. Okay, and this is the last part. This is a bit far-fetched, but I would like to end our class with some crazy idea for you to think about, right? The problem with solar harvesting is that you can only use the sunlight during daytime, and in some country, daytime is only 4 hours. In our country, it's a bit better. It's 8 to 9 to 10 hours, right? But in some countries, it's only few hours. So that's very wasteful of the solar energy. So what they do here, the concept proposed almost 100 years ago, that can we make the energy harvester in space? This origami style solar panel that now NASA is developing. They make an origami style, and then when it go to the space, it unfolds to big solar panel, right? So the idea is very simple. They convert the solar energy, which is 24/7 in space. You don't have daytime, nighttime, because it moves with the sun, right? So they harvest 24/7. They convert that solar energy into microwave, and then they beam it to the earth, right? And on earth, you have this kind of receiver antenna to receive that microwave and convert it back into the microwave converted back into the DC and feed to the grid. And this is really far-fetched idea, but it's quite exciting to think about, because now you can harvest energy 24/7, and there are many other benefits. For example, in the solar harvesting, the solar irradiation on Earth is only 1,000 watt per square meter, but in space it's 1.4. So many more solar can be harvested. Availability is only 29%, daylight average in some country, and on space is 99%, right? 24/7. There are some laws, in terms of like beaming solar energy, but the target for them is about 75 to 90% efficiency. So that's what they're trying to achieve. And the initial cost is quite high compared to harvesting on Earth. Harvesting in space, the cost would be so high, right? But the advantage is like this, right? And I will not talk about the advantage because I already talked about it, but here is the challenge, right? The reason why this idea is not being used nowadays, the cost is very high, right? But with Elon Musk being able to reuse the rocket, maybe the cost will be cheaper and cheaper. So imagine if in the future we have the satellite around the world that can help beaming this energy, free energy to the earth to be used. That would be really exciting opportunities, right? But another thing that is difficult is when you beam this kind of beam to the earth, you need a large antenna to accept this energy and convert it. So that also the problem because you put the infrared beam, I don't know what will happen to human brain or whatever, right? So that's something we have to figure out. And because it deal with space, international regulation governance need to be considered. Okay, so that's the crazy idea that I would like to talk about to end the class. And let's recap, right? We talk about the fundamental of the thermodynamics of solar utilization. High energy photon is being utilized and released as a form of lower energy photon, and that release give us the work we want or give us electricity, right? And the light in and light out is equal. That's why the world doesn't get hotter. But now we have the greenhouse effect. That's why when we try to irradiate the smaller energy photons, the high entropy photons, then it get reflected back because of the greenhouse effect, and that slowly warmer the earth. But in reality, without the greenhouse gas, the earth should be the same temperature in and out. Right, and we discussed mostly this picture, right, where the first two class we discussed about the photocatalysis, the solar fuel synthesis, solar to fuels, right? We discussed the techno economics of it. If you missed any class, go check the classes. And we discussed how difficult it is to do water splitting or to do water oxidation. So we replaced that water oxidation with organic oxidation. And we discussed the benefit of that in terms of energy requirement reduction and so on, right? And we also discussed that another part of the wavelength, like the IR, the heat can be used for different processes. And these two processes, two key energy conversion device can be combined and can be constructed into the hybrid device to make better solar energy utilizations. And these are the topics that we discussed throughout this course, right? Solar to electricity, solar to chemicals, solar to energy, solar to thermal, and then chemical, and then electricity, mineral, solar to food, solar to water. So these are the topics that we discussed. I think it covers most of the solar utilization, and I hope that Professor Paravi part and my part give you a really broad and with some concrete example of how we can better utilize solar energy beyond the just electricity. And you have the know-how now when you talk to people to say that, oh, solar energy is not just electricity, but it can do so much more. So I hope that gives you an overview and some idea for your projects and some idea for your future deployment on solar related projects. So I mentioned this again, the final exam is 35 points and the homework